Today I'll be talking about the scanning tunneling microscope, or STM. The STM experiment consists of a tip that has a voltage applied to it and a semiconductor that is guided through a gold plate. A current runs from the tip to the semiconductor. This current is fixed so that the tip moves depending on the topology of the sample. The energy structure of this experiment consists of a band gap with a quantum well and a barrier. The tip is placed with an energy higher than the gap, and electron tunnels, gets trapped in the well, combines with a hole, and emits a photon in some direction. But what is the structure of the semiconductor that we're using? The structure is very complicated and includes many layers with different materials, but for the sake of our explanation we can use a simpler model. Indium gallium nitride is sandwiched between gallium nitride layers. The indium layer is our well, and it's where the electrons get trapped. But what happens to the photons? The photons are transported with a fiber optics cable and sent to a photomultiplier that gives us a count of how many photons were emitted. We then scan a small area of the sample with a resolution we set, and generate a picture based on the luminescence at each point of the area, with darker areas emitting less light. Since a fixed current makes the tip move up and down as it scans, we can also generate an image with the topology of the sample, with lighter areas being peaks and darker areas being holes. This is important because it can give us a picture of the sample and can be used to determine if there are any inhomogeneities. If high enough voltage or current is used, a modification is made in the sample as it is being scanned. This is what the profile of the modification looks like, and it can be anywhere from 8 to 90 nanometers in depth. This is important because a gradient of modifications with different spacings and sizes can then be made, which has many applications such as modifying the light inside the LED. One of my experiments was to try to make the modifications as small and as close to each other as possible. Chemical analysis was done on the modifications to figure out what elements were being removed from the surface. The X-ray emission from the modified surface and the unmodified surface were compared. This is what the output looked like. The most interesting parts were the peaks, which sometimes showed differences. This is gallium, this is nitrogen. While the results were not exactly what we were expecting, we still got some useful information out of this. But modifications are a bad thing when we don't want to create a gradient, especially since it can affect the luminescence of the LED. We wanted to try something to stop this modification, so we covered part of the surface with 2 nanometers of palladium and intended to modify it. The results were interesting to say the least, as we weren't exactly sure what some of the lines we created were. We believed the high current was oxidizing the palladium which caused this.